Okay, so we are going to start the third chapter here, with the first section being over transformations of quadratic functions, and this whole lesson chapter will be about quadratics. I'll discuss that here in a bit. Okay, and one learning target, which is that you're going to be able to graph as well as describe transformations of quadratic equations in vertex form. Okay, a couple definitions is that a quadratic function is a function that can be written in the form the function of x is equal to a times the quantity of x minus h squared plus k. As long as a doesn't equal 0, really you're often going to see quadratic functions also in this form, and we'll talk about how to graph these ax squared plus bx plus c. You definitely should have seen this in your Algebra 1 class, although my guess is you'll need a good bit of refreshing. Okay, so basically anytime you have a variable with an exponent of 2, it's considered a quadratic function, quadratic equation. So, the U-shaped curve, or the U-shaped graph of a quadratic function is called a parabola. So you're going to want to get used to that word. Basically, this whole chapter is going to be about graphing. So we will have quite a bit of work to do with parabolas. Okay, so this is kind of like another activity, actually very, very similar to what we did at the end of Chapter 2 and 2.5. So I'll kind of walk you through the original one, and then I'm going to ask that you work through these other ones and try to get some of the patterns figured out for yourself. So let's just go ahead and graph this first one. Okay, so here I just have the quantity y is equal to x squared. I'm going to graph a couple ordered pairs in my table, and then I'm going to actually graph them on the graph. So here I have a separate sheet of paper that I can just show my work on, so you all have a little bit of an idea how to do this. Okay, so here we have y is equal to x squared, and we want to start when x is equal to negative 2, just because that's that first one I want to fill out. So that means I just need to write, well, my y value is equal to my x value, negative 2 squared. Okay, and so then it's going to be helpful to remind everybody, what does it mean to square a number? It means to multiply it by itself. So this here is negative 2 times negative 2. That's what it means to square. So negative 2 times negative 2 is a positive 4. So there is my first ordered pair, negative 2, 4. Okay, let's do the next one. When x is equal to negative 1, means y is equal to negative 1 squared. And y is equal to positive 1, because negative 1 times negative 1 is positive 1. What about when x is equal to 0? That means y is equal to whatever 0 squared is, and 0 squared is 0 times 0, so this is 0. Okay. And then x is equal to 2, y is equal to 2 squared. I don't need parentheses around this 2 because there's no negative to really confuse me. This is just simply 2 squared, which means 2 times 2. Where this one here, I kind of have to have the parentheses because I have this negative 1 squared, and negative 1 times negative 1 is positive 1, where this is not the same as if I had y is equal to negative 1 squared. Because the order of operations, what this would tell me to do is this would tell me to square 1. So 1 times 1 is 1, and then take the opposite of it. So this one would be equal to negative 1. So it's important to know like when the parentheses are necessary. So like if you're ever squaring a negative number, you do need parentheses around it. That will matter. Okay, let's go ahead, and 2 squared is the same as 2 times 2, which is 4. Okay, and it looks like I accidentally skipped over x's 1. That's no big deal. This will just be equal to 1. Y is equal to 1 squared. And then 1 squared is just 1. Okay, so let's go ahead and graph these ordered pairs. Negative 2, 4. So let's go ahead and get to the graph. Okay, and hopefully you have those written down. So the first one is negative 2, 4. So negative 2, negative 1, negative 2, 1, 2, 3, 4. Okay, what about negative 1, 1? Negative 1, 1. Then 0, 0. Then 1, 1. Then 1, 2, 1, 2, 3, 4. Okay, and I just happen to know it's also going to go through here. So let's just notice some things about this graph here, because this is, like we talked about in the previous section, y is equal to x squared is the parent function. This is the parent function to all quadratic equations. So that means this is like the most generic basic curve that we're going to have. So let's just take a look at it. Okay, it's got a vertex or a lowest point at 0, 0. Okay, and then it goes up by 1, and then up 1 over 1, and then it goes up over 1, and then up 3. And then over 1 and up 5. You may notice some differences here. But really, the big thing is, like, we want to look at about, like, where is this vertex positioned? It's also opened up and kind of has a standard, like, width to it. So similarly to the 2-5 activity that you all did, what I would like you to do is take the time to go ahead and not only find the y values for each of these tables given these functions, I would also like you to go ahead and give a descriptor about what this like new extra stuff. So if you look at all of them, they're all kind of like the parent function with one little extra part. So this one has a little +2. So once you graph this, I want you to tell me, what do you think this +2 does? Here, it's basically the same thing, except for it's x minus 3 in parentheses. After you graph all of this, why don't you tell me what like this -3 does? Same with this -1/2. So why don't you all pause the video and go ahead and work on that right now, and then we'll kind of go over that in total when you are done. Okay, so I'm assuming that we've already paused the video at this point and went ahead and just kind of filled out the table. So here's the numbers that you get. Okay, and then what I want to do is I want to go through, we're going to graph each of these, and then together collectively, hopefully you can look over your work and figure out what you did or did not do. We can compare it to the parent function, which is y is equal to x squared. Okay, so first off, this black one here is the parent function. Okay, so that is just y is equal to x squared. Okay, so let's go ahead and do the red one. The red one is -2, 6, -2, 1, 2, 3, 4, 5, 6. Okay, -3, or -1, 3, -1, 1, 2, 3, 0, 2, 1, 3, 2, 6. Okay, so let's kind of go ahead and take a look at this one, red. Okay, all right, and then this is y is equal to x squared plus 2. Okay, so let's just kind of look at this this red graph to black graph. Like, what do we think this +2 here contributed to the parent function? What did it do to the parent function? Well, as I look at this, like, so it kind of goes up 1 over 1 and then up 3 over 1. Okay, so that is the same as this. So as far as width, or it doesn't really affect it. It didn't make it narrower, it didn't make it wider. But it's like starting location, right? This one started at 0, 0, and it appears that this one's kind of starting at 0, 2, like 2 units above. So if I kind of observe each other point, they've all just been shifted up. Okay, so this particular one shifted it up 2. Okay, now very, very similar to absolute value. This moved it up 2 because it's +2. So what do you imagine -3 would do here? If I had -3, what do you imagine it would do? Well, we kind of connote up with positive, so that means up is kind of this 2, and the number 2 is, 2. So -3 would kind of tell me down, and 3 units because it's -3. Okay, so this number out here is going to tell me up or down. Okay, that number out there is going to tell me up or down. Let's go ahead and move on to the next one. Okay, the next one here, we have a -3 on the inside. Okay, so -3 on the inside here. of the parentheses. So let's go ahead and graph these ordered pairs. So I start with 1, 4. So 1, 1, 2, 3, 4. Okay. And then 2, 1, 1, 2, 1. And then 3, 0, 1, 2, 3, 0. And then 4, 1. And then 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. Okay, so here is... Okay, I just want to get another point so I can kind of graph this accurately. Here's the blue line, or blue curve rather. Okay, and then this is y is equal to x minus 3 squared. Okay, notice that it is on the inside here. So let's go ahead and take a look. What happened here? Well, again, it kind of has that pattern of up 1 over 1 and then up 3 over 1. So it doesn't have a slope, definitively a curve. Whenever that slope between points is not constant, that tells you that it's a curve. It's not increasing at a steady constant rate. But if we look at the vertex point, okay, this vertex point is the highest or lowest point. Sometimes it will be a lowest point or a highest point. If we look here, it looks like it was just kind of moved to the right 1, 2, 3. Okay, so let's just take a look at this point. Was this moved to the 3 units to the right? 1, 2, 3. It was. This one here. 1, 2, 3. 3. 1, 2, 3. Yeah, okay. So this one has just been shifted to the right 3. Okay, and so this one is the one that's backwards. It actually functions the same as absolute value. So if you took the time to get that figured out, it's going to pay dividends here because, normally we would think minus 3 is going to tell you to the left 3 because minus you tend to associate more to the left on the graph. But there is a reason why. Again, I'll address that even though it's the exact same reason why a minus 3 tells me to the right 3. But this will shift your graph left and right. Okay, and that's this inside the parentheses plus 3 minus 3 plus whatever number. Okay, let's do the last one. I'll do this one in black and then I'll highlight it so we can definitively tell the difference. Looks like we have a negative 4, negative 8. So negative 1, 2, 3, 4, negative 8. It's right here. Then we have negative 2, negative 2. So that's right here. 0, 0. So 1, 2, and then 2, and then 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this one here. Okay, if we look at this one here. Okay, I think there's one big obvious part here about what this one does. Okay, and that obvious part is that it's not opening up the same direction. Okay, so that's the more obvious part there, right? It's opening down as opposed to all the other ones are opening up. So this one will cause it to open up or down. And for the same reasons with absolute value, up is going to be when that number outside is a positive value, down when it's a negative. We can see we have a negative. That's what it causes to open down. Okay. And then the next one is, it does appear to be a little bit wider, like it's, it shoots out, like, when I'm 2 units to the left away on the parent function, I'm 4 units up or down. So here, when I'm 2 units away, I'm like 2 units down. So that is telling me that I have different widths. So this one will cause it to be wider or narrower. Okay, so this is the number itself here will tell you whether it's wider or narrower. The open up or down will just tell you whether positive or negative, okay? And we'll formalize all of that actually right here. Just keep this on hand. So, which brings us to what vertex form is. Vertex form is y is equal to a times the quantity of x minus h squared. So x minus h is together. And then plus k. So a is that highlighted value that we just did. So let's go ahead and start with that. Okay, as we talked about just a moment ago, okay, it's going to cause, a is going to cause it to open up. Okay, it will cause it to open up when the a value is greater than 0 okay, which for, everybody, that means that a value is positive. If a is greater than 0, that means it's positive, right? Because 0 is neither positive nor negative. A less than 0 is going to have it open down, okay? It will open down, okay? It will open down when my a value is less than 0, meaning when my a value is negative. Okay, so just like the absolute value, I'm going to be able to look at the graph and I'm going to be able to tell a whole lot about what this graph looks like without doing one thing, without using a calculator or my computer or doing it by hand. I'm going to have a majority of these transformations figured out. So you can start and just look at this a value outside of the parentheses and just be able to tell, is it going to open up or is it going to open down right off the bat with very little work done. Okay, so if it's positive, up, negative, down. Okay, so the next thing is we will be able to tell whether it is wider or narrower. Okay, we can tell whether it's wider if the absolute value of a is going to be less than 1. Okay, so that means that when the absolute value, so you don't have to look at positive or negative, you just look at that number, its absolute value, its distance from 0, and say, well, if that number's close to 0 or less than 1, it is going to be wider. It's gonna slow its growth. It's gonna make it wider out. Where, as opposed to, it's going to be narrower when the absolute value of a is greater than 1. Okay, so when that absolute value of a is, it's going to increase faster because it's multiplying by a larger number, so it's going to increase it faster, as opposed to when it's less than 1, it's going to actually kind of decrease that amount because multiplying by fractions less than 1 decrease the amount of your result. So that's kind of why. Okay, so again, we should just be able to look at all of this and be able to tell a lot about the graph without actually ever graphing anything. Okay, H, again, is the one that is tricky. Okay, this is the one that just you tend to mess up because it does seem a little bit backwards, okay? So I'm going to try to represent it the best I can, but once you think about it a little bit, it does make sense, okay? So when the H value is what moves the graph left or right. But the thing you have to keep in mind is that the basic form of vertex form says X specifically minus H. Okay? So it says minus is what it is. So we need to think about when my H is going to move it to the right. It's going to move it to the right when H is greater than 0, meaning it's positive. Okay, so when my H is greater than 0, it's going to move it to the right. But you got to be careful about what that's going to look like when H is positive. When H is positive, inside of the function, what you are going to see is you are going to see x minus a number squared. Okay, it looks like it's going to be negative, okay, but it's not. But the H value itself is positive, is what I meant to say. It says, yes, it's going to say x minus a number, because when I plug a positive number in there, it's going to say x minus. So if I plug in positive 2 for H, it's going to say x minus 2. And that will move it to the right. Where it will move it to the left when my H is less than 0, meaning it's negative. Okay, so let's think about what if H was negative 2. That would move it to the left too. What is that going to look like in the function? When it looks like in the function, it's going to say x minus negative 2. Well, how do I typically rewrite minus and negative? Hopefully, you're thinking to yourself, when I write minus and negative, that is going to be addition. So this is the one that makes it a little bit tricky. When H is negative, it is going to show up as x plus a number, and when H is positive, it's going to show up as x minus a number, which is honestly, it's just backwards. If you want to remember this one as, oh, whenever this one's backwards, or when this is positive, it's left, and negative, it's right, that probably will do you fine. But this is kind of the details of exactly why that happens. But it can also be kind of confusing. So, all right, let's go ahead and do k, the k value is going to move it up and down. Okay, it's going to move it up when my k value is greater than 0, meaning it's positive. Okay, so when k is greater than 0, it's positive, and then it will move it down when your k value is less than 0, meaning it's negative. Okay, and so this is all displayed, and hopefully you kind of came to this conclusion anyway on your own when we did this little activity here. This number outside here by itself is going to move it up or down. This number here, it's going to open it up or down. It's going to be wider or narrower. This number on the inside of the parentheses is going to move it left or right. Okay, so let's go ahead and describe some of these transformations on our own without actually graphing and seeing what these look like. So let's go ahead and we can just go A, H, K. So let's start with my A value here. My A value is -4. So let's just start whether that's going to open the graph up or down. Okay, so I'm going to try to squeeze as much of this stuff on the screen as I can. Doesn't look like I'm going to get it all. That's fine. Okay, it's going to open up when the A is greater than 0. So what is my A value? My A value is -4. Okay, and that is less than 0, right? -4 is less than 0. So this means it's going to open down. Okay. All right. And then we just have to determine, is it going to be wider or narrower than like the general parent function? Okay. Compared to y equals x squared, which is the parent function. What is that going to do? Well, what's the absolute value of -4? Well, it's +4. So is that greater than 0 or greater than 1 or less than 1? Well, 4 is greater than 1, so this is actually going to be a little bit of a narrower graph. Okay. What about x minus 2? So when x minus 2, my h value is positive, right? When my h value is positive, I'm going to plug it in. It's going to say x minus 2 when h is positive 2. Again, this is a little bit confusing, right? Because, like I said, when h is positive, it's going to show up in your function as x minus your number. Okay, so this means this is going to move it to the right 2 units. And then lastly, a +5 outside of the parentheses, separate from everything else, is, well, that k value is 5, which is greater than 0, so that means it's going to move it up. Up 5 units. Okay, so already, compared to where this graph normally starts, we know it's going to move to the right 2 and down 5. It is going to open up, and it's going to open up a little bit narrower than all the other graphs. Or this one's going to open down. I misspoke. Okay, let's do h of x. So h of x, when I look at A is a positive number, so that tells me it's going to open up. All right, and then also as I look at this, I want to look at the absolute value of this, right? The absolute value of this is 1/2. So 1/2 is going to be, let's think. So 1/2 is, the absolute value of that is 1/2. That's less than 1. Okay, and if it's less than 1, it's going to be a little bit wider. Okay, this +3 on the inside here, okay, really means my h value is a -3. So my h value here is -3 because when I plug in a negative number for h, when I plug in negative number for h, it's going to be x minus a negative, which is just an addition. Again, if you want to memorize it as x plus a number, that's going to be moving it to the left. That's fine with me. This is going to move it to the left 3. And then a -9 here is going to have it moved down 9 units. Okay, so these are just as important as the absolute value ones, and it's very it's literally the same thing actually. Just how the graph moves is different. Okay, so why don't you pause the video, try A, which has 2 parts, g of x and j of x. Go ahead and try those ones on your own and check them with me right now. So I'm assuming you've already done these. You're just trying to see what your work is doing. So this one is going to open down. because my a value here is negative. That a value is also, the absolute value of it is less than 1, so it's going to be a little bit wider than the normal graph. This plus 1 here means my h value is negative 1, so this is going to move it to the left 1. And then this plus 3 here is going to shift it up 3 units as well. Okay, j of x. This is a positive number, so it's going to open up. Okay. The absolute value of this number is 2, which is greater than 1, meaning that this graph is going to be narrower than most of them. Narrower than, not most of them, but the parent function is what I should say. Okay, minus 5 means my h value is a positive 5, which would shift it to the right 5. Also, when it's just x minus a number, that means it's going to go to the right. Right 5 units, and then minus 6 on the outside is going to shift it down 6 units. Okay, that's the transformation. So that when we look at our learning target here, which was I can graph and describe transformations of quadratics. One, they go hand in hand. That's why I put them together in the same learning target. But when I say describe transformations, I'm literally meaning this, what we just did. Okay, but when we actually go to graph these here, you're going to use those descriptions quite a bit. So let's go ahead. Let's graph each quadratic function, then identify the domain, range, minimum, maximum values. Okay, and I will discuss all of that extra stuff that we haven't really talked about. So let's just think about the parent function. Okay, so that parent function is the black one without the highlighted here. And the thing about the vertex is that vertex always started at 0, 0, right, of the parent function. So the parent function always starts at 0, 0. So based on the transformations telling me left and right, that means I can figure out where that new vertex is at. That's why this form is called vertex form. It very easily tells you where your vertex is shifted to. Okay, so there's another thing about it, though. If you kind of look wherever that vertex is at, so let's use the blue line, for example, here. There is a line of symmetry here that all the other points are like reflected across, right? 1 to the line, 1 away from the line, 2 to the line, 2 away from the line. So there's also an axis of symmetry. And where does that axis of symmetry go? It always goes through this vertex point. So once you found the vertex, you found like probably the two most important things. You can find the vertex, and then you can also find that axis of symmetry. So that's kind of the first two things you always want to find, is you want to find the vertex, then the axis of symmetry. Okay, so let's describe how this graph has been moved. Okay, so here, I know my h value here is equal to 3, meaning it's been moved to the right 3. And then the k value here is negative 4, meaning it's moved up 4. So here's the great part, is if you know what your h and your k value are, if you know what they do, it tells you where the vertex is at. So I know that the vertex is normally at 0, 0, but my new vertex for this problem here has been shifted to the right 1, 2, 3, and not up. This should be down 4 because it's negative. So right 3, 1, 2, 3, and then down 4. 1, 2, 3, 4. And what is this ordered pair? This ordered pair is the ordered pair 3, negative 4. H and K, which we'll talk about that here. Actually, let's go ahead and mark that down below as a note. See where it says vertex? We actually just found that. Okay. In red, I'm going to put H comma K. For us, it's 3, negative 4. Okay, so now let's get out our ruler, because our graph always has an axis of symmetry. Okay, so this axis of symmetry here will always, always, always go through the vertex. So once you found the vertex, it is going to go through that. It's going to be a straight up and down line, and it will go through the vertex. All right, and there's my line. It will always be the x is equal to h line. And for us, that is x is equal to 3. That's the line where my x value is always 3. Okay. So now all we have to do is find the other points. For me, in general, you need 5 points. Okay, for me to consider the graph completed. I want to see 5 points exactly. There will be exceptions where like maybe the graph starts really high and then also goes up. But in general, I want to see 5 points. But really, if you get 3, you get 5. And I'll explain exactly how you get that. Well, the first one is going to be your vertex always. So we've already got 1. We just need 4 more. So let's go ahead. And what you want to do next is you want to pick x values near your axis of symmetry. So I have an axis of symmetry of 3. So I can either pick x value 4 or x value 2. It doesn't really matter which one because of the symmetrical pattern that we'll see here, because you'll get the same number actually whether you pick 2 or 4. We'll see that though. And it doesn't matter. For me, I'm going to pick x is 2. I'm going to pick x is 2 because I tend to like to deal with smaller numbers. So let's go ahead, and I want to find the y value when x is equal to 2. Okay, when x is equal to 2, that means I want h of 2, which is equal to 2 times 2 minus 3 squared minus 4. Okay, so that means h of 2 is equal to. Now, here's the thing with me. If you want to be able to do this by hand, feel free. I'm actually just going to show you how to use the calculator to get this, so there's like less work for you to do. Kind of under the assumption that this is some, like evaluating an expression like this is something we should know how to do at this point. Okay, so here what I'm going to do is I'm just going to write this expression in the calculators exactly as it's written. 2 times, using parentheses, 2 minus 3. And then I'm squaring outside of that parentheses, minus 4. Okay, so let's just take a look here and see how they're written literally the exact same. And I get negative 2. So when x is 2, y is 2. So that gives me an ordered pair 2, negative 2. 2, negative 2. Okay, and so then once I've graphed that, the thing that's nice is that 2, negative 2, the symmetric property, right? Since these things are symmetrical figures, that means once I have 1 point, I actually get one for free because I can reflect it across my axis of symmetry. So it takes 1 unit to get to the line. It's going to take me 1 unit to get away from the line. Okay, so again, this goes into that concept. Once you have 3, you'll have 5 because 1 is going to be itself. Once you get 1 more, then you get the third one for free. Now we just have to find the next ordered pair. Okay, so you want to think again about these ordered pairs, specifically the x values, right? So I already have a y value for the x is 2, and I also already have a y value for the x is 4. So the next one I could pick 1, or I can pick, that's 3, 4, or I can pick 5, right? I can pick 1 or I can pick 5 because I've already used 2, 3, and 4. So I'm going to pick 1 because, again, I like to deal with small numbers. So when x is equal to 1, that means h of 1 is going to be equal to 2 times 1 minus 3 squared minus 4. That means h of 1 is going to be equal to, let's go ahead and we can basically, if you hit second and then enter, what it will do is it will just copy what you had previously written, and then all I have to do is go in here and hit 1. Replace that 2 with a 1. Otherwise, you could just retype it in. Okay, and again, see how this right side is written the exact same way on my calculator as it is on my paper. to get 4. So I now have the ordered pair 1, 4. 1, 1, 2, 3, 4. It takes 2 units to get to my line. It takes 2 units to get away from my line. Okay, so this is my graph here. It's a parabola. It is a little bit narrower than like any of the other ones that we've had. Okay, and then try to not make it a straight line. Try to make it a curve if possible. It's not going to be perfect. Okay, yeah, so let's make sure it kind of checks. We know it was shifted to the right 3 and down 4, as we said here. This tells me it's going to open up because a value is positive, which it does. And then since this number 2 is greater than 0, that's the value if it's greater than 0, it's going to be a little bit narrower. So that checks all of our boxes. Okay, let's go and figure out some of these other things. We already talked about the vertex. It's always what h and k is. Now we want to find the maximum or the minimum value. Okay, and again, you're going to get that from the vertex. Okay, so your minimum here or maximum is going to be, it's going to be your k value. Okay, so what was my k value? My k value here was -4. Okay, so it's always your k value, but for me it's -4 because that's what my k value was right here. Okay, but let's see what that means physically on your graph. It means where is your maximum point or your minimum point. So for example, if we look at our graph, it kind of starts here and then it goes up. And it's going to go up forever. It's never going to stop going up. It's just going to keep going and going and going. So do I have a value that I hit and say, boom, there's the highest point possible? Well, no, because it goes off forever into infinity. So it doesn't actually have a ceiling, but does it have a floor? It does have a floor, right? And that floor can be seen right here. So, so that is my minimum value because there are no points lower than this. This is the absolute lowest spot. There's no points that are lower than this. They're all here or above it. And for that, what I would like you to do is you just circle whether it's a maximum or a minimum. If it's a lowest point, it's a minimum. If it's a highest point, it's a maximum. Ours is a lowest point, so it's a minimum. And that minimum value is -4, and that's your k value. Okay, let's talk about the domain. Okay, so the domain is going to be your x values. So it's going to ask, essentially it's asking the question, what x values can be used? That's whenever you have the domain of a graph, that's basically the question you're asking. What x values can be used? So is there any reason why I can't use an x value? Well, we haven't really seen any examples where there's x values that you can't use, but those will come. But if you look at this one, I mean, if you got to give me a good reason why I couldn't plug a certain x value in here. Really, you can plug all of them in here. And you can physically see that on the graph is as I start at my minimum here, there's no holes or gaps in my graph as I go off to the right. As I go off to the right, yeah, it shoots off of my graph, my physical graph here, but there's still a y value that goes with it. Same here. So that means I can use all of them. Okay, so that means I'm going to use the set of x values such that x is a real number. Okay, so this is what we call a set notation, which means the set, I'm going to read it again. This means the set of x values such that x is technically this means an element of, but is a part of a real number. So as long as I'm picking x values that are like real numbers that you've heard of, it's going to work. You'll find a y value that goes with it. Okay, range. Range is a little bit different because instead of what y values can I use, that's not really, it's more like what y values can be produced. So based on the x values that I can use, what y values can be produced from that? Is there any y values that can't be produced from that? So as I move left and right, I can plug any of these values in. But as I move up and down, are there any y values that can't be used? Well, I mean, we can just kind of scroll. Well, I know I don't even have to really consider up off of the graph because I know this graph shoots up forever, so those y values have all been hit. So as I kind of go down, I'm using all of these y values, but until I get to this spot, this is my pivotal spot, right? Because I do have a minimum and there's no ordered pairs below it. So is there y value, like, is there anywhere this graph has a y value of negative 10? No, there's not. And same with negative 5 or negative 4.1. It has a floor. And that floor is going to be very important. So if you notice, this vertex is very important to some of the questions we want to ask. Okay, so let's figure out what y values can be produced. Okay, this is going to be this set of y values because my range is going to discuss my y values such that my y values are all greater than or equal to negative 4. Okay, set of y values such that y is greater than or equal to negative 4. So how did I get all of this? Well, I found my minimum value. My minimum value is negative 4, right? And so at negative 4, all my y values are above that, which would be greater than. And the only one that's not greater than it is itself, which means it's equal to. So all my y values start at negative 4, and they're all greater than that. None of them are less than that. So these are the y values that can be produced. Okay? And this is kind of like the fancy set notation. But realistically, when you're describing your domain and range, I really am not going to be too picky as long as you can really describe what x values are being used and what y values can be produced out. I'm not going to be too picky about that. Okay, I do know there's an example here, but I do want to do the next. You know what? I take that back. I'm actually going to do letter B for you, and then I'll just let you all do C and 3 on the next page, okay? Okay, the process is the same, okay? It's a little tedious at first, but again, if you know your transformations, it's going to go a lot faster. So, okay, we know that my h value here is going to be equal to negative 2, right? Because I have a plus 2 here, so that means that my h value is negative 2. That's what would cause the plus 2, meaning it's going to be moved to the left 2. And that my k value here is positive 1, meaning it's going to move up 1. Okay, so I know that my graph normally starts at 0, 0. But instead, this one's being moved to the left 2, left 1, left 2, and then up 1 also. So this is where my graph is actually going to start. Okay, now let's go ahead and draw our axis of symmetry. I like to just do a little dashed line right through it because I always have it dashed because this line technically isn't part of the graph, but it's just so convenient to us that there's not really any reason to not use or utilize it in some way. Okay, and this is the what line? This is the x is equal to negative 2 line because that's where all my x values on that red line are negative 2. Okay, so next I just need to find x values close to the graph. Okay, now the only thing that, and it just happens to be fractions, but they get a bad rap. That tend to throw students off, especially when they're graphing. Most students really, really like whole numbers to get out, and you know what? I prefer myself in that camp as well. Okay, so this is kind of the trick that I've kind of figured out is that I'm multiplying by 1/2, so whatever this denominator is, that's how many units away you want to work from the axis of symmetry, and that's what you want to pick for x values. So, for example, since my denominator is 2, I want to pick x values multiples of 2 units away from my axis of symmetry. So, what x values are 2 units away? Well, I could pick 0, or I could pick negative 4. Either one of those is going to work fine. I'm going to pick x is 0. So, x equals 0. Means I want to find g of, where's my red pen here, 0, which is going to be equal to negative 1/2 times 0 plus 2 squared plus 1. Okay, Now this one with the fractions will look a little different in your calculator, but not a whole lot. I mean, I don't think it's a huge stretch by any okay, so let's go ahead and clear all this out. Hopefully it's not dead yet. It's been on low batteries for months. Okay, when you have that fraction in front, and we've seen this before in my class, put parentheses around that, please. More than likely, the way you would type it, you would get the right answer, but for me, I just feel very safe having that parentheses around and grouping that as -1/2 together. Okay, so I have -1/2. That is representing this -1/2 here. And then I still have to go 0 plus 2 in parentheses, and then square that parentheses, and then go plus 1. And then I get the ordered pair -1. So g of 0 is equal to -1. So I have the ordered pair 0, -1. 0, -1. Okay, and then I can reflect this across 1, 2 units to the line, 1, 2 units away from the line. Okay, and this is actually really, really good sign because I know in the back of my head that this graph is going to open down because of this negative a value, and I also know that it's going to be a little bit wider than the other graphs that we've dealt with because this value's absolute value is less than 1. So all of these little subtle things are going to be really nice when it comes to getting yourself acclimated to what's going to be good signs for this graph as well. Okay, now I have to pick another x value to reflect across the axis of symmetry. And again, since I'm dealing with a fraction, this denominator is 2, so I want to pick x values that are multiples of 2 units away. So I don't want to pick x values that are 1 units away or 3 units away. I want to pick x values that are 2 units away, and then another 2 units away, or 4 units away, or 6 units away, or 8 units away, multiples of 2. Okay, so I have a couple options. I can pick x value as, well, I've already done 0. I can pick x value 2, or I can do x value -4. I already did that, x value -6. And either one of those is going to get me the proper y value, and then I can reflect it across. Again, I like dealing with small, or numbers closer to 0 is really what I should say. So lower value numbers, but I'm going to pick x value as 2. I think that would be best. So x value is equal to 2, which means I want the g of 2. And I guess I haven't talked about this. It might be good now to talk about this. G of 2 just means the function g when x is 2. This is the function g when x is 0, and the value of that is -1. It's just kind of a fancy say of y value. Anyway, so here I have -1/2 times 2 plus 2 squared plus 1. Okay, let's just throw that in the calculator. Okay, again, you can go ahead and hit second enter, and it will just pop up what you previously wrote, and then instead of 0, I want it when x is 2. And I get -7. So g of 2 is equal to -7, meaning the function g, when x is 2, the y value is -7. It's kind of just the short. That's why I love math. It allows you to be so lazy, but you can disguise it as being, maybe smarter than I actually am. All right, so let's go ahead and graph this. So x is 1, x is 2, and then y value -1, -2, -3, -4, -5, -6, -7. Now I just have to reflect this across my axis of symmetry. 1, 2, 3, 4 units to the line. That means it's going to take me 4 units to get away from the line. 1, 2, 3, 4. And this graph is definitely wider than the other ones. It's opening down, nice and symmetric looking. Okay, so let's go ahead. Let's do the domain. What x values can be used? Well, is there any x value I can't use? No, I can use all of them. Fun fact, folks, for quadratic equations, it's always all real numbers. There's never going to be, it's a different kind of function if there's going to be a hole in your graph or an x value that you can't use. The y value, though, the range definitely changes. So the y value here, we kind of have a ceiling, right? We have a ceiling here at 1, meaning that my range is different. I can produce y values starting at 1 and I can produce y values less than that on each side. So I'm going to say that my range is the set of y values such that y is, in this case, less than or equal to 1. Now, the other one was greater than, but that's because the graph was opening up. This one is less than because my graph starts here and goes down. Okay, my vertex is what ordered pair? Well, you could just find it on the graph, but it's also your h value comma your k value, which is -2, 1. And then lastly, my graph has, this one has a maximum. Okay, it has a maximum because it has a ceiling. It has a highest maximum point, and that maximum point has a value of 1. Okay, that's it as far as the type of problems I'm expecting you to do from this lesson, folks. So these ones take some practice. I really, truly believe that they're not all that rigorous or difficult, but they definitely are going to take some practice. So what I want you to do is pause this video. You can try number 3 and letter C here on your own, and then check it with me here in a moment when you are done. Okay, so I'm going to fly through this a little bit quicker than normal, just so we can get the video wrapped up. So let's go ahead and check it out. So this one here, I have an h value of +4, which is right 4. And a k value of equal to 6, which is up 6. Okay, so right 4, up 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. That is my vertex. And I know that this is going to be a maximum because I'm looking at this -3 here. And that is big red flag that my graph is going to open down. I seem to have misplaced my ruler. There it is. Alrighty, and so now I'm drawing my axis of symmetry. Okay. Which is the x is equal to 4 line here, because that's where my x values are. Okay, and then now I just have to pick x values close. It's a whole number, so I can just pick x values units of 1 away. So I'm going to start with x is 3. Say q of 3 is equal to -3 times 3 minus 4 squared plus 6. Here, -3 times 3 minus 4 squared plus 6. Let's go to my error. Oh, I just didn't hit 6. It's 3. So q of 3 is 3. Ordered pair 3, 3. 1, 2, 3, 1, 2, 3. And then reflect that across. And then next I'm going to pick x is 2. So that means q of 2 is equal to -2 times 2 minus 4 squared plus 6. So that means q of 2 is equal to, and then here I can just hit 2 to get -6, okay. 2, -1, 2, 3, 4, 5, 6. Yes, this one is very narrow because this 3 values, absolute value, is far from 0. Okay. Okay, so here's my graph. That's what the graph looks like. I did this curve on the right was done terribly. Apologize. Okay, let's do the domain. I can use every x value. There's not one I can't use. The domain will always be all the real numbers. Okay, let's do the range. The range, so this one is a maximum value. What's it max out at? Okay, it maxes out at 1, 2, 3, 4, 5, 6. It maxes out at 6. So my y values start at 6, and they're all less than that. They all move down. So that means that my range here is going to be the set of y values such that y is less than or equal to 6. My vertex is the ordered pair 4, 6. H4, K6. And like I talked about here, I have a maximum value, and that maximum value is 6. All right, and so then I'll just kind of gloss there for one more second so you can check it, although you should be able to pause the video and see at any point. So, okay, so this one here is going to open up, and it's going to be wide, pretty wide. And my h value here is -2, so that's left 2. My k value here is -3, which is down 3. Okay, so we're going to start in the graph. We normally start at 0, 0, and we're going to go left 2, down 3. Left 2, down 1, 2, 3. Okay, there's my vertex. Let's get my axis of symmetry. Okay, here my denominator is a 4. So that means we can pick x values that are units 4 away from my normal x value. So this is x is equal to -2. So let's pick x values 4 units away from that. So here's -2, -1, 0, 1, 2. So let's pick x as 2 to start. 2 is 4 units away from 2, or from -2. So g of 2 is going to be equal to 1/4 of 2 plus 2 squared minus 3. So that means g of 2 is equal to, I believe that's -2, but we'll double check. Okay, so here I want to type this exact thing in. So I'm going to put parentheses around 1/4. And then I'm going to go 2 plus 2 squared, and then minus 3, which is 1. Oh, yeah, because 2 plus 2 is 4. 4 squared is 16. 1/4 of 16 is 4. 4 minus 3 is 1. Okay, so this is 1. And then 1, 2, 3, 4. 1, 2, 3, 4. Okay. Okay, now the next one I'm going to pick is going to be like 8 units away. Hopefully it fits on the graph. If not, we can maybe try something in between. All right, so 2, 3, 4, 5, 6. So we're going to pick x as 6. So that means g of 6 is equal to 1/4 of 6 plus 2 squared minus 3. I don't think this one's going to fit on the graph, but that's fine. This will be a good example of seeing how fast these graphs grow. All right, so we're going to go here, but instead of 2, we're going to pick 6. And yeah, we're going to get 13. So that means when x is 6, 3, 4, 5, 6, this graph is going to be like 3 units off. So it's going to be like up here, give or take. Okay, which would be right about here as well. Okay, now this we can see is definitely wider. I'm just going to pick x as 0 in the graph and the calculator real quick just to see if we can have, if something nice and neat pops up. I think it should. Yeah. So when x is 0, y is -2. And so then that just gives us a little something else to work with. Otherwise, this other method works fine. But this would be an example where if you gave me 3 points, I would probably take it because you kind of showed your work. And some of the numbers go off the graph, and you just did the best you can. Okay. So let's go ahead here. Nice and gradual parabola here. Shooting up. Here. Okay. Not perfect, but close enough. Point taken. Okay. Domain, again, is always all real numbers. You can use every x value that you're aware of to this point to graph y value here. Okay, so let's go ahead and look at the y values. So this y value here is more of a floor. Okay, here it's got a floor of -1, 2, 3, -3. Yep. So that means my graph starts at -3 for the y values and then kind of goes up. Meaning that all my y values are going to be greater than or equal to -3. I have a vertex. My vertex is the ordered pair -2, -3, h comma k. And here I have a minimum, right? I have a lowest point, and that lowest point is -3. Okay. Alrighty, so this unit here is very similar to the absolute value, has a lot of similarities, but ultimately there's going to be some differences, and some of the problems take a little bit of time, but nothing too crazy. Otherwise, that's it for today's lesson. Why don't you move on to the homework, and I'll see you for the next lesson 3.2.